e to the power minus mv squared over 2 kbt dv. ये आएगा क्योंकि इसके नॉर्मलाइजेशन पर इसको मैं ऑलरेडी ए इस्तेमाल कर चुके होंगे आप, मैं इसको बी कह देता हूँ, ठीक है। वह बी इज इक्वल टू क्या, बी इज इक्वल टू 4 square root of m cube over 8 by kb cube d. सही है? From 0 to infinity. सही है? अच्छा, I'll give you another rule for integrating exponentials, ठीक है? So the integral from 0 to infinity of x cube e to the minus alpha x squared is equal to 1 over 2 alpha squared. ठीक है? Equal to 1 over 2 alpha squared. So that's alpha. So this is equal to 1 over 2 beta लिखी देते हैं 4 square root of m cube over 8 by kb cube d cubed times alpha 1 over alpha squared, ठीक है? 1 over alpha squared किस इक्वल होगा? यहाँ आ जाएगा, तो बता दो मुझे क्या आएगा यहाँ? 2 kbt by m क्या आएगा? हाँ, ठीक है। तो क्या आता है इनमें? इसको सिम्प्लीफाई कर सकते हैं आप लोग? टर्म्स कैंसिल करते हैं। जल्दी जल्दी जल्दी। कर दिया? मैंने कर दिया। So that gives 8 kbt over m, ठीक है? The expectation value of velocity, ठीक है? The last expectation value that we want to calculate is the expectation value of v squared, ठीक है? The expectation value of having v square speed, ठीक है? That becomes equal to beta integral 0 infinity तक of क्या हो जाएगा? b to the power 4 e to the minus mv squared over 2 kbt d. Right? We need another rule. So I'll give you another rule. So the fifth rule that we have is the integral from 0 to infinity of x to the power 5 e to the minus alpha x squared is equal to 3 by 8 square root of 5 over alpha to the power 5. Clear? That's the fifth and last rule that we need for this lecture, hopefully. So that means that the expectation value of v squared becomes equal to 4 square root of m cubed over 8 by, ये आप ही साथ साथ करते रहें ताकि मैं जब भी करूँ तो आप ठीक कर दें, ठीक है? इसको मल्टीप्लाई करने 3 by 8 से dot 3 by 8 and then you have to multiply by the square root of pi times alpha power 5. So that's 32. So it's pi times 32 kb power 5 t to the power 5 over m to the power 5. ठीक है? Over m to the power 5. ठीक है? So इसको जल्दी से सिंप्लीफाई करने क्या आता है? The expectation value of v squared is equal to क्यूब है, वहाँ क्यूब। देखना एक चीज तो क्लियर है कि n में kb रह जाना है, kbt ऊपर रह जाना है, ठीक है, क्योंकि पावर 2 है, ये 1/2 है,
3 kbt over है,
क्या है
3 kbt over है,
थैंक यू, 3 kbt over x, ठीक है। तो compare this to our previous result. The expectation value of having a velocity in the x direction was the square of that was kbt over m. The expectation value of having a speed v square, the expectation value of v square, and having a speed v, and the expectation value of v square is 3 kbt over m. Okay, it's quite obvious why we have a factor of 3 here now, right? Because you sum all this, right? Because it's vx squared plus vy squared plus vz squared. Okay, that's why you have a factor of 3. That said, okay, we are now in a position to calculate the kinetic energy. So we can now calculate the kinetic energy. Kinetic energy is of course half 1/2 m. अच्छा, actually I'll be a bit careful. I want to find the expectation value of the kinetic energy. So I'll write it in brackets, the expectation value of the kinetic energy. We should be careful about, okay, we're talking about expectation values. ठीक है? The expectation value of kinetic energy is half times the mass. अच्छा, is it the expectation value of v square या the expectation value of v square? Is it the expectation value of v whole square या is it the expectation value of v square? क्यों? वो तो हमने कहा था कि वेलोसिटी स्पेस के अंदर dv का वॉल्यूम क्या है, लेकिन काइनेटिक एनर्जी जो है, ठीक है, मैं ये देखिए ना, एक्सपेक्टेशन वैल्यू ऑफ v होल स्क्वायर जो है दैट इज 8 kbt over m. The expectation value of v square is 3 kbt over m. Say, huge difference. You can't just square this and get that. Okay? Taking the kinetic energy, the average value of the kinetic energy depends upon the expectation value of v square. क्योंकि given a velocity v, the kinetic energy is half mv square. Given lots of possibilities of velocities that you can have, v1, v2, v3, v4, the expectation value of the kinetic energy would be, kinetic energy एक दफा निकाल के एक v के लिए, फिर दूसरे v के लिए निकाल के, तीसरे v के लिए निकाल के, सबको probability से मल्टीप्लाई करके निकालेंगे ना, तो जिस चीज की एक्सपेक्टेशन वैल्यू आएगी वो v स्क्वायर की आएगी, एक्सपेक्टेशन वैल्यू v होल स्क्वायर नहीं आएगी, ठीक है? It's easy to make this mistake, लेकिन ठीक है, there's a difference. Right? मैं कह रहा हूँ कि if you kinetic energy is half mv square, right? Where v is right now, v is the speed. It is possible to have a different speed, and for every speed you will have a different value of the kinetic energy. Okay? And the speed you can have is the probability of a given speed is given by f of v dt. If you, let's say, had 10 different speeds and we had 10 different kinetic energies, every time you sample the system, you measure a different speed and it has a different kinetic energy. Every time you sample, right? So you say कि मैंने 10 दफा sample किया है, expectation value क्या है? आप सारी kinetic energies का mean लेंगे ना? जब kinetic energies का mean लेंगे तो expectation value किस चीज़ के बाहर आएगी? v square के बाहर आएगी. v की expectation value whole square नहीं आएगी. ठीक है? The kinetic energy is that, so it's half mv की expectation value, v square की expectation value. So that's 3/2 kBt. That's 3/2 kBt. It would have been nice for us to have this result probably in the first 2 or 3 lectures of the course. जब हम ideal gas कितने हमने काम किया था, लेकिन at that time we had not studied the canonical ensemble. We needed to understand the canonical ensemble and the Boltzmann factor and the fact that different energies की probability जो है वो Boltzmann factor से scale करती है. We needed to understand this in order to be able to derive this relationship के the kinetic energy, the average kinetic energy of a gas molecule in an ideal gas is 3/2 kBt. ठीक है? अच्छा. It's a very, very important result. And this is something you should know. This is something you should know. I don't always say you should know things, but you should know the Boltzmann factor, you should know this result. Answer. Since an ideal gas doesn't really have any other kind of things going for it, its kinetic energy is sort of equal to its internal energy. Right? So the energy you can say is equal to 3/2 kBt for a gas molecule. For ideal gas molecule, ignoring rotational and vibrational energy. Take it just because of its translational motion. Furthermore, the energy for, let's say, the energy for an Avogadro's number of molecules would be equal to what? 3/2 Na kBt. ठीक है? Which would be equal to 3/2 RT. ठीक है? So that's the energy. That's the internal energy of an ideal gas, of 1 mole of an ideal gas. ठीक है? So if you have 1 mole of an ideal gas at a temperature T, the internal energy of that system is 3/2 RT. ठीक है? Once again, a very fundamental result which we should be aware of. तो आपको याद होगा कि कोर्स के स्टार्ट में यहाँ तक ठीक है कैसे आया क्या है कोर्स के स्टार्ट में we proved actually that the internal energy of an ideal gas only depends upon its temperature, right? We proved it how? We said that du is equal to dq plus dw, ठीक है? And we saw that u was for an ideal gas, we saw that du जो था that was always equal to n times cv dt, ठीक है ना? Changes in u were always equal to n cv dt, ठीक है? याद है? नहीं क्या? And you can see that we have reconfirmed that result today because we've seen that the energy of an ideal gas of one molecule, the Na molecule, is just equal to 3/2 RT. R is just the gas constant. T is the temperature. So it still just depends on the temperature. Okay? We re-derived this result. Right? Achha. So du is equal to NCV dt. Okay? How is CV defined? This is what was CV? CV is heat capacity at constant volume . molar heat capacity is the amount of energy you need to give to heat 1 mole of to raise the temperature of 1 mole of gas by 1 degree Celsius. So for let's say n moles, for n moles, okay, U is 3 by 2 nRT. Say BU is equal to 3 by 2 nR dt, okay, which is equal to NCV dt. Right? So the heat capacity of an ideal gas at constant volume is then 3 by 2 R. The heat capacity at constant volume of an ideal gas is just 3 by 2 R. Okay? For a monatomic ideal gas. Okay, we'll look at diatomic gases next time. Okay? So we now know that CV is 3 by 2 R. If CV is 3 by 2 R, what is Cp? The heat capacity of constant pressure. So what about heat capacity at constant pressure? How do you find it? If you go back to your notes, you'll find that we derived a relationship between Cp and Cv. We derived that Cp minus Cv is equal to Nr. Okay, but there is a number of moles. So for 1 mole, Cp is R plus 3 by 2R, which is equal to 5 by 2R. Okay? So Cp is 5 by 2R for an ideal gas. So the heat capacity at constant pressure is 5 by 2 times the universal gas constant. What does this mean? Physically, it means that if you have a balloon, okay, and let's say that a balloon can expand, so if you give 3 by 2, and let's say you have 1 mole of gas inside the balloon, then if you give it 5 by 2 R amount of joules of energy, the balloon will expand, okay, and it will also increase its temperature by 1 degree Celsius, right? Because the balloon can expand, the pressure is constant. Okay? If instead of a balloon you had a pressure cooker, okay, as I said, the volume cannot expand, and you wanted to raise the temperature of the gas by 1 degree Celsius, you have to apply 3 by 2 R joules of energy. Okay? If you want to raise the temperature in a closed container, you use this. Okay, with fixed volume. If you want to raise the temperature in an open container or a container which can change its volume such that the pressure is constant, that is the heat capacity. This we derived, you can go back and look at it. It's very interesting that you need to give less energy at constant volume and you need to give more energy at constant pressure. Why? It follows from the first law. Because when you conduct a process at constant volume, dW is 0 for an ideal gas. So all the heat that you give goes into increasing its temperature. But if you conduct the process at constant pressure, then volume will change, right? So some of the energy you give goes into changing the volume, and the rest of the energy goes into changing the temperature. Very like that. Okay? Hence, you need to give more temperature at constant, more energy at constant pressure, and less energy at constant volume. जी. नहीं. They're both per mole. हाँ. तो किधर? हाँ. नहीं वो तो कैंसिल हो जाता है. She's right. हाँ.
CP minus CV has to be equal to just R.
Cp minus Cv is equal to Nr, as far as I can remember. It's Nr, not just R. I'll double check this for you. ठीक है? मैं double check कर सही है.
Sir, even if it is NR,
हाँ.
it is NR, but like उसमें भी ये होगा कि CV will be NR number one, CV won't be NR.
हाँ, मैं ये सोच रहा हूँ. मैं इससे आता हूँ. हाँ, मैं इसी पॉइंट पर मैं ये सोच रहा हूँ. सही है. I think you're right. हाँ. लेकिन मैं डबल चेक करता हूँ. ठीक है. अच्छा. The last thing that I wanted to talk about was कि आपको याद होगा कि हमने adiabatic processes के लिए we had P gamma was equal to a constant, right? हमने derive किया था where gamma was equal to Cp over Cv. ठीक है? We now have a value for Cp over Cv which is equal to 5/3 for an ideal gas. ठीक है? So now if I ask you to draw a PV diagram, ठीक है? Now if I ask you to draw a PV diagram for an adiabatic process, you know कि उसका gradient किस तरह होना चाहिए. ठीक है? एक गामा जो है वो 5/3 है, तो PV गामा तो you have to plot a constant over v to the power 3 5/3. ठीक है? Finally, by definition ना, ठीक है? By definition, Cp and Cv are usually defined per mole. Then so it depends on whether you're talking about molar heat capacity or heat capacity of the gas. If you talk about heat capacity of the gas, okay, then yes, this will be more. But if you talk about the molar heat capacity, it's always for 1 mole by definition. Okay, na? So Cp would have for it's defined. So define it. So now you have a value for that. But I think this pretty much ties up everything that we talked about for an ideal gas pehle. Because there were a couple of gaps which we could not fill then because we had not done the canonical ensemble. Okay? So next time what we'll do is we will look at the equipartition theorem and we'll start assigning energies to degrees of freedom. ठीक है? इस केस में आप देखें, we basically found is that the kinetic energy is proportional to 3 kBt/2. ठीक है? And we found we had velocity in the x, y and z direction. ठीक है? If you had so this is lecture 12. The last time we did 3 things. We did the Maxwell relations. Maxwell relations of thermodynamics. ठीक है? We looked at how free energy and chemical reactions are linked. ठीक है? And the third thing that we looked at was the thermodynamics of an elastic rod. ठीक है? So we look at these three systems. So today what I want to do is I want to take a step back to something we've already done, and so I'll just write down the purpose of the class before. So the purpose of the class is to derive that the energy per molecule of an ideal gas is 3/2 Boltzmann constant times the temperature. ठीक है? The internal energy of ideal gas. ठीक है? So that's the purpose. And इस class में we will use one approach to derive this, and in the next class I will use and derive the equipartition theorem. ठीक है? And we will derive the same relation in a different way. ठीक है? But then we will not be limited to a monoatomic gas, whereas in this lecture we will be limited to a monoatomic ideal gas. ठीक है? The internal energy of ideal gas. So I'll tell you what our assumptions are. Okay? So our assumptions. Okay, assumptions are, of course, there is an ideal gas. So that means that it has no intermolecular forces. Okay? We have elastic collisions, and they're not very frequent. ठीक है? So we assume that we have a gas, and the gas is ideal. There are no intermolecular forces between the molecules of the gas, and there are and they don't collide very often. ठीक है? And so the actual gas molecules themselves have an infinitesimally small volume. ठीक है? Even though the gas itself has a volume V. अच्छा. So we will neglect rotational and vibrational oscillations. Yeah, energy. ठीक है ना? मतलब if a molecule is rotating at some frequency, of course it has some energy. If it is vibrating at some energy, it has some at some frequency, it has some energy. We will neglect the rotational and vibration energy of the gas molecules. ठीक है? So we'll assume it's an ideal gas. We neglect rotational and vibration oscillations. And third assumption, which is the most important one in helping us doing the maths for this, is that we assume that every molecule behaves like a small system in contact with a reservoir. We assume that every molecule behaves like a small system in contact with the reservoir, where the reservoir is all the other gas molecules that it's with. Okay? Reservoir, which is all other gas molecules. Okay? Then if I were to pictorially show you what the system looks like, then what you're basically saying is that we have some volume. Okay? This is our special gas molecule which we are looking at. Okay? And then there are all these other gas molecules around it. Okay? Collectively, which define the reservoir. Okay, does that make sense? Okay. So the equivalent statement for this is that we have a reservoir at temperature T, और ये जो हमारा छोटा सा गैस मॉलिक्यूल है वो हमारा सिस्टम है जो कि रेजर्वोयर के साथ हीट एक्सचेंज कर सकता है या एनर्जी एक्सचेंज कर सकता है. ठीक है? So what you said is that we want to look at the kinetics of a single gas molecule in an ideal gas. ठीक है? हम single gas molecule की बात कर रहे हैं, and will model it such that we neglect the rotational and vibrational oscillations. We will consider these in the next lecture when we do the equipartition theorem. Okay? For now, we just assume that we have purely translational motion. We have translational motion. Okay, we have translational motion. And so we want to show that because of this translational motion, the internal energy or the kinetic energy of the gas molecule will come out to be 3 by 2 kBt. We just want to derive that relation for now. Okay? So we've assumed that this system looks like इसके हमने क्या terminology दी थी इस तरह के सिस्टम हमने किसी को याद किस तरह का इंसान था ये canonical
कर रहा हूँ
so we say this system looks like it's a canonical ensemble. Why is it a canonical ensemble? Energy fixed नहीं है मतलब system की energy fixed नहीं है. The system can exchange energy with its surroundings, but its temperature is fixed. ये जो molecule है, it can collide with other molecules and it can exchange energy. ठीक है? The fluids are elastic. ठीक है? So this is exactly how जो आप याद है हमने hydrogen atom का जिक्र किया था in एक reservoir के साथ हमने Boltzmann distribution derive की थी वहाँ से. Exactly वही condition है. ठीक है? Total energy. Reservoir plus system is fixed. So ET जो है, that is energy of the reservoir plus the energy of the system. That is fixed. मगर energy of the system जो है, that can be exchanged between the system and the reservoir, keeping this constant. तो इस केस में हमने कहा था, अगर आपको याद हो, हमने कहा कि the probability of the system having an energy EI, yani the probability of our pink gas molecule of interest having an energy EI is given as e to the minus EI by kBt over z, where z was the partition function, okay? Where z was summation I goes from 1 to n e to the minus EI by kBt. Okay? Where n is the number of states accessible to our molecule, right? In terms of energies. यही था ना? ठीक है? Where z is the partition function. We have said that is equal to the kinetic energy of an ideal gas, which is equal to its internal energy, because there are no potential effects inside the ideal gas. Okay? So if I'm interested in finding out the kinetic energy of a molecule, of a single molecule in an ideal gas, the expected kinetic energy, expectation value is zero. So what do I need? I need its velocity. Okay. Achha. So if let's say I have a box and inside this box I have my molecule of interest, okay, and it's going in a particular direction, and let's call its velocity v0. Okay, let's call its velocity v0. Now, I can define my axes as this can be my x-axis, this can be my z-axis, and this can be my y-axis. So in general, this velocity has three components: Vx, Vy, Vz. Say, right? So, in any given direction, okay, x, y, or z, I can define. याद है ठीक है ना? So I can define a velocity distribution function and I call it g of vi, okay, where I can be x, y, or z. So it can be g vx, g vy, g vz, such that gvi, so such that gvi dvi gives you the fraction of molecules with velocity vi in the ith direction. What does this mean? Okay, what it means is that if vi is, let's say I is x, so vx, the function g of vx times dvx tells you the fraction of molecules which can have a certain velocity in the x direction. Okay. GVx, GVx is a continuous distribution, we assume. Okay. Hence, at any given point, its value is 0. So you have to multiply it by dx to get a non-zero answer. Okay. So GVx dx, if I just write it down, so आप उसको टोटल नंबर से मल्टीप्लाई कर देंगे तो आपको पता अगर आपको क्योंकि यू वांट टू हैव अ प्रोबेबिलिटी डेंसिटी फंक्शन you multiply the probability density function by the total number of molecules, you get the expected number of molecules that have a particular velocity. ठीक है? We want to do it independent of the number of molecules, right? So we're just saying the fraction of molecules. ठीक है? We want the probability. Once you have the probability, you can just multiply it by the number. अच्छा. तो just to clarify, so g of vx dvx is fraction of molecules with velocity vx in x direction. ठीक है? अच्छा. Now we know that the energy, kinetic energy, is half mv squared. If we talk about velocities in the x direction, then the kinetic energy of a molecule in the x direction, so that's proportional to, let's say, half mvx squared. The reason I've written proportional is because a molecule can simultaneously have velocity in the x, y and z direction. Okay, let's say वो एक diagonal पे जा रहा है, but its kinetic energy is proportional to half mvx squared. Its total kinetic energy is, of course, the sum of all the velocities squared, right? So its kinetic energy is proportional to half mvx squared. So yeah, that means its energy is proportional to half mvx squared. If its energy is proportional to half mvx squared, it means that the probability of having a velocity vx is proportional to what? If its energy is proportional to half mvx squared, okay, then the probability that a molecule can have that energy is proportional to the Boltzmann factor. Because in the end, this molecule is like a system connected to the reservoir. Okay? So, the probability of this energy is proportional to e to the minus ey kVt. So the function g of vx square, okay, that is of course then, because of that logic, proportional to e to the minus mvx squared by kBt to 2 kBt. सही है? ठीक है ना? तो basically then, if I plot this, ठीक है? If I plot this, if I plot Vx on the x-axis, and if I plot g of Vx, then where does it peak? Peaks at 0, ठीक है? Because 0 पे exponential goes, बाकी हर जगह it falls off. So this looks something like that, ठीक है? And at higher temperatures, the probability of having a high velocity goes up, ठीक है ना? If you increase t, because the exponential falls off slightly slower. Notice that Vx can have positive or negative values, ठीक है? Because it's a vector quantity, ठीक है? So g of Vx is proportional to this factor e to the minus Vx square over 2 kBt. We require g of Vx to be normalized. I require it to be normalized. If I require it to be normalized, how do I normalize it? I require g of Vx to be normalized. Right, so I just integrate. I integrate what it's proportional to. Okay? It's proportional to e to the minus mvx square over kBt dvx from minus infinity to infinity तक, ठीक है? From minus infinity to infinity. अच्छा, what does this come equal to? अच्छा, पता है, so इस lecture में ना I need to perform about 5 infinite integrations of exponentials. So I'll dedicate one board to just to like the laws of integrating these things, right? So I'll just write it here. It'll take us ages if we derive them, so I'll write it. So if you have an integral from minus infinity to infinity of e to the minus alpha x squared dx, किसके इक्वल होता है? पाई बाय अल्फा, ठीक है? तो we'll use that here. तो इस केस में अल्फा किसके बराबर है? माइनस m ओवर या 2 का फैक्टर मिसिंग है, ठीक है? माइनस m ओवर 2 kBt के बराबर है, ठीक है? जी हाँ मैंने माइनस करा था, हाँ सॉरी, ठीक है, हाँ. अच्छा, तो this becomes equal to square root of pi times 2 kBt over m, ठीक है? तो this integral becomes equal to this factor. I require g of Vx to be normalized, hence I can write a g of Vx square that is equal to square root of m over 2 pi kBt e to the minus mvx square over kBt. ठीक है? What have we derived here? We derived something quite nice actually, if you think about it. What we've derived is that given a gas in any volume, ठीक है? This factor allows us to predict if you know the temperature, ठीक है? then you can say something about the number of molecules that will have a certain velocity in the x direction. Okay? So it's a useful quantity. We will derive two more useful quantities now using this. So now I have my probability density function basically. I multiply g of Ex by dx, I get the number of the fraction of molecules that can have a velocity Vx. Okay. So let's calculate some quantities that we will need. Let's find the expectation. What would the expectation value of Vx be? ठीक है? कैसे निकालूंगा? इंटीग्रल माइनस इंफिनिटी तक Vx g of Vx ये होगा ना? ये किसके इक्वल होगा? ये ट्रिवियल है। Vx किसी भी v की एक्सपेक्टेशन वैल्यू ये जीरो होगा। ये जीरो क्यों होगा? क्योंकि g is an even function, ठीक है? Vx is an odd function, right? So you multiply an even function by an odd function, you integrate, you get zero. ठीक है? So the expectation value of Vx is zero. Let's find the expectation value of Vx squared. क्योंकि ये हमें चाहिए होगा बाद में। Vx is odd क्योंकि plot y is equal to Vx. It's that, right? So that's an odd function. Right? लेकिन g is an even function. जिसे हमने plot किया है। So an even function times an odd function का area under the graph over all values of the domain is zero. मेरे पास प्रोपोर्शनैलिटी है इसके साथ, ठीक है? जी से प्रोपोर्शनल लेता है। मैं अगर डायरेक्टली इंटीग्रेट करता हूँ तो दिस इज व्हाट आई गेट आउट, ठीक है? लेकिन आई वांट द इंटीग्रल ऑफ दिस, आई वांट द इंटीग्रल ऑफ दिस। इसका मॉड्स पे इसकी प्रोबेबिलिटी नहीं है, ये प्रोबेबिलिटी है। दिस इज नॉट अ वेव फंक्शन, है? दिस इज अ प्रोबेबिलिटी डेंसिटी फंक्शन। इट्स इसके अंदर आप डी से मतलब आपको प्रोबेबिलिटी इसी से मिल जाती है। इसका मॉड्स पे नहीं है, बिल्कुल सही। इसमें जाके आप क्या करेंगे वो नहीं करना। अच्छा, तो द एक्सपेक्टेशन वैल्यू Vx स्क्वायर जो है now becomes equal to the integral from minus infinity to infinity Vx square g of Vx dx, ठीक है? अब इस केस में मुझे एक और जाहिर है रूल चाहिए कॉम्प्लेक्स इंटीग्रेशन का, क्योंकि अगर मैं कह दूं कि a is equal to square root of m over 2 pi kbt, a is equal to square root of m over 2 pi kbt, ठीक है? So this becomes equal to a integral of Vx squared exponent of minus m Vx squared over 2 kbt dvx, ठीक है, ये है ना. तो I'll write down the second rule for complex for the integral of the Gaussian function. Minus infinity to infinity तक you have x squared e to the minus alpha x squared dx. ये किसकी इक्वल होता था? हैरान हो किसी को याद होगा वैसे. ठीक चल 1/2 अल्फा तो है ना, अल्फा है कितने हो गए? 5 by alpha cube. अब एग्जैक्टली है क्या था? ठीक है, अच्छा. तो so that becomes equal to इस केस में अल्फा वही डिनोमिनेटर में अल्फा यानी कि न्यूमरेटर में आ जाएगा 8 kb क्यूब t क्यूब और डिनोमिनेटर में आएगा ये जाएगा स्क्वायर रूट ऑफ m ओवर 2 by kb t, ठीक है, टाइम्स 1 over 2 square root of 5 times 8 kb cube t cube over m, ठीक है. ये आता है ना, the expectation value of the square of the velocity in a particular direction. Okay? तो ये स्क्वायर रूट ऑफ m है, ये m का 3/2 है. यहाँ से 4 निकले तो 2 आ जाएगा, कट जाएगा, ठीक है. तो dx स्क्वायर कहते देखिए किसकी इक्वल आता है, उसको सिंप्लीफाई करें. चलिए टर्म्स कैंसिल कर दिए हैं. एट बाई से कट जाएगा, m 3/2 है मुझे. हाँ अच्छा, तो क्या आएगा kbt by m, ठीक है. It's slightly closer to what we were trying to get towards. It was 3/2 kbt. It's approaching that. We're not quite there yet. So that's so that's the vector velocity. Like that's the expectation value of the component in the x direction. Okay. If you repeat this calculation for Vy squared, what will you find? You find the same, kbt over m. If you repeat this for the for Vz squared, once again you will find kbt over m. ठीक है. So the expectation value of the square of the velocity component in every direction is kbt over m. Fine. These quantities are important to us and you will use them afterwards. ये करने के लिए we'll just take them here. Right? So we have looked at velocities. Now what I want to do is I want us to look at speed. ठीक है? And I want to derive something called the Maxwell-Boltzmann speed distribution. ठीक है? I'm going to derive the answer for the speed distribution. When I talk about speed, what I mean is that I no longer want the vector, I want the resultant. ठीक है? I want the magnitude. So I want v, which is the magnitude of the vector velocity, where vector velocity is an undefined condition. ठीक है? I want the speed. So speed, of course, is a scalar. Doesn't depend on direction. You can imagine that if we think about stuff in velocity space, यानी कि if you plot vx, so if you plot it in velocity space, ठीक है, यानी कि आपके एक्सिस जो है this is vx, vz, vy, ठीक है? Then what shape would a small speed dv have? What shape would a small speed dv have? V is a vector. V itself is a vector, right? So I have, let's say, some vector velocity. I have a vector velocity. Where this is velocity. Okay. If I change v from v the vector to v plus dv the vector, okay, the speed is the magnitude of the vector. So the magnitude is the same across a shell of radius v, right? So if I construct a shell of radius v, let's put a shell where I have the speed, I have the same speed. If the velocity goes from v to v plus dv, we have a volume of 4 pi r square dv. So the velocity changes from v to v plus, and let's say this vector, if this is v1, this is v2. So let's say if v2, if mod v2 is equal to mod v1 plus some d mod dv, okay? So the volume in speed, in velocity space, the volume of dv is proportional to 4 pi r squared dv, yeah, 4 pi v squared dv. So this is from 4 pi v squared dv. Does that make sense? Okay, if you increase your velocity by dv, the volume is 4 pi v squared dv. Okay? The volume of states that are accessible to you. Okay? So we had defined a velocity distribution function. Similarly, we can define a speed distribution function. Okay? So we define a speed distribution function. Okay, and we call it f of v dv, which tells us the fraction of molecules that have a speed between v and v plus dv. Okay? So it tells us the velocity that have speed between v and v plus dv. Now, because the volume is proportional to v squared, the volume of speed you can access is proportional to v squared. Okay? So f of v dv जो है, ठीक है, that is proportional to v squared times the exponent of mv squared by 2 kbt. इसके बारे में सोचने देना. क्या ख्याल है? So when you talk about speed, ठीक है? Absolutely, it's over the entire volume, right? Because speed is just the magnitude of the velocity. Where velocity is vx, vy, vz. So if the speed changes from some initial v to some v plus dv, in velocity space, you are integrating over the whole shell, this new shell which you've created of volume 4 pi v squared dv. Okay. So the fraction of molecules that can have a speed v, okay, fraction of molecules that can have a speed v are proportional to v squared, okay, v squared times the exponent of minus mv squared over 2k. Okay? Because the vector velocity is proportional to minus half mv squared over kbt. Lekin speed is proportional to v squared times that. So hence we get v squared times e to the minus mv squared over 2 kbt. Does that make sense? Say? Say nahi say? ठीक है? सही? क्या confusion है? सही. So let's normalize. ठीक है? Once again, I want the integral of v squared e to the minus half mv squared over kbt dv, where v is speed now. V is speed. Okay. What do I want this to be equal to? I want it to be equal to 1. Let's say आता क्या है पहले, फिर उसको 1 over करके माना जाएगा. Limits क्यों होनी चाहिए इस इंटीग्रल? Limits क्या होनी चाहिए इस इंटीग्रल की? हाँ, तो speed is the radius ना. ठीक है, वो कहाँ से कहाँ तक हो सकता है?
0 to infinity.
Over all space में क्या है? Velocity. dv is velocity. देखिए, I had a 3-dimensional space of velocities. ठीक है? Every component of the velocities, the probability of having that component scaled as e to the minus half mv square over 2 kbt. Now I'm talking about speed. Speed we said is basically उस space के अंदर speed की जो probability है dv में, v plus dv में कुछ speed है, that is proportional to v square times the probability के velocity vx, vy या vz उस magnitude की होती है, right? ठीक है? Right? तो this factor the factor है ना v square e to the minus mv square over 2 kbt dv. This factor tells you the fraction of molecules that can have the speed between v and v plus dv. Okay? अकेले क्यों ऐसे है? So I want to now find this integral. This integral is इसकी limits क्या होनी चाहिए? 0 आपने ठीक कहा. 0 से लेके कहाँ तक? मुजाहिद ने पूछा इंफिनिटी क्यों? अच्छा सवाल है. इंफिनिटी इसलिए क्योंकि once again this is one molecule related to a reservoir. ठीक है? बिल्कुल. And a molecule can have an infinite velocity with a very small probability. We have said that the probability of having any energy is e to the minus ei over kbt. even a very high velocity has a very small probability, right? So for any velocity less than infinity, there is some probability. So for any speed less than infinity, there is a probability v square e to the minus mv square over 2 kBt. Right? Hence, we have to integrate over all possible speeds, so from 0 to infinity. Right? क्योंकि we assume that we have a gas that is connected to a reservoir temperature T, and the reservoir can give as much energy as you need, right? With some probability that's scaled as a Boltzmann factor. So yeah, that's all. So we need our third rule for integrations. So we now have an integral from 0 to infinity of x squared e to the minus alpha x squared. ऐसे ही है ना, right? X squared e to the minus alpha x squared है. This is just equal to इसी का हाफ होगा ना, क्योंकि इवन फंक्शन है. एक इवन फंक्शन का इंटीग्रल कर रहे थे माइनस इनफिनिटी से इनफिनिटी तक, तो और मतलब उसी इवन का 0 से इनफिनिटी तक उसी का हाफ हो जाएगा. X is equal to 1/4 square root of pi over alpha cube. Clear? So this factor then becomes equal to 1/4 square root of मैंने पहले लिखा था सारा कुछ आएगा pi 8 kb cube t cube over m cube. सही है? ठीक है? तो f of v dv becomes equal to 4 square root of m cube over pi 8 kb cubed d cubed. सही है? अच्छा, this thing that we've derived here, this is a very important result in kinetic theory of gases, okay, and it's called the Maxwell speed distribution. So if you ever come across the term the Maxwell speed distribution, that's what it is. What important that multiplied by e to the minus m v squared over 2 kBt dv. ठीक है? Thank you. ठीक है, तो you plug in V and you plug in the temperature, ठीक है, and you get a number out which tells you the probability क्या है कि यह speed होगी इस molecule में, ठीक है? It's an extremely useful quantity, ठीक है ना? आप देखें, मतलब all we know is the temperature, हमने सिर्फ temperature specify किया है और उससे हमारे पास एक probability आ गई कि molecule की क्या velocity होगी, क्या speed हो सकती है, ठीक है ना? It's a very powerful result अगर सोचें इस बारे में. तो ये कहाँ से आया? ये आया बोल्ट्जमैन स्टैटिस्टिक्स से, ठीक है? अच्छा, तो what we can do is that we can find some more important expectation values. कंटिन्यू करते रहिए, थोड़ी सी ब्रेक चाहिए आपको, चाहिए या करते रहे? चलिए इस पर रिफ्लेक्ट कर लें थोड़ी देर, ठीक है? तो we start at 5:30.